Welcome back, folks, and let us jump into part two of bonding. As you recall from last time, we said that we have bonding, right? And what is bonding? We said bonding is what? Forces of attraction, forces holding different atoms together, right? And we said, hey, this is really what? The nucleus of one atom, nucleus of one atom attracting valence electrons of another, right? Of another. Good. And then we said, hey, what is the cause? Why does this happen? Um, Atoms gain stability. Stability through bonding. And how do they gain stability through bonding? By lowering their potential energy, right? The atoms have less potential energy when they're in the bond than when they are out of the bond. And that makes them more stable. And what's the general process? Atoms do what? They acquire a noble gas configuration. Noble gas what? Noble gas electron configuration. How? By gaining, losing, or sharing valence electrons. Good. So that's kind of an overview of bonding. So let us move on. Here we go. Consider NaCl and H2O. What type of bonding exists in each? Okay, more notes. Here we go. We want to talk about types of bonding. And there's some type over here called metallic, and we'll get into that later in the chapter. And there's some over here called covalent network, and that's kind of a special case, and we'll talk about that later in the chapter. But the two we're going to focus on right now are covalent and ionic. So let us get into covalent and ionic. What is an ionic bond? This is a bond, the way I like to define it is, this is an electrostatic attraction. Electrostatic attraction. What is electrostatic attraction? That means an attraction between what? Positive and negative. An electrostatic attraction between positive cations, that's a little redundant since cations mean positive, between positive cations and negative anions, which form a lattice, which then form a lattice. Good. Now, how does this process really occur? Well, I have a metal, and the metal loses electrons, and when it loses electrons, it becomes a cation. And then I have a nonmetal, and where do I find the nonmetals? Hey, right side of my periodic table, upper right. Nonmetals do what? A nonmetal gains electrons and when it gains an electron, that means it's gaining negative charge, and so it becomes an anion. And then what happens? What do you know about positives and negatives? The cation and anions, since they're oppositely charged, they do what? They attract each other and form the lattice. Cool. Now, what's a lattice? Do you guys understand what a lattice is? I think of it kind of like a chain link fence made up of cations and anions. So we'll take something like NaCl. Na is a metal, right? So what's going to happen? That metal is going to lose an electron. Oops. that's a negative, and become Na plus. Cl is a nonmetal. It's going to gain an electron and become a Cl minus. And then what happens? My Na plus and Cl minus attract each other. But I don't just have two of these guys. I have a whole bunch of them. So that means I would have an Na plus, but it will be attracted to a Cl minus, which is attracted to a, oops, wrong color, which is attracted to an Na plus, which is attracted to a Cl minus, and there's another Cl minus that's attracted here, and another Cl minus that's attracted here, and then an Na plus that's attracted to these Cl minuses, and I get a whole big network of positive and negative ions, and this is what we call a lattice. So that is my ionic lattice. And so I really don't have just NaCl. No, really I have, whenever you see this NaCl, what you really should think is, wow, I've got this whole lattice of Na pluses and Cl minuses. Good. And once again, how do I think, when do I think ionic? I think ionic when I see a metal and a non-metal. Good. Covalent, on the other hand, in covalent, I have nonmetals, so it is bonding. Well, let's give it a nice definition, in which nonmetals share electrons, and they form a molecule. Not a lattice, just one little piece, right? And so the example that we will use is water. Consider I have a big oxygen here, and then I have a couple hydrogens. Now they actually share electrons, meaning their electron clouds will overlap, right? So we'll let these represent my electron clouds, right? And so this area here where it's overlapping would be the actual bond. Good. Now on the oxygen, we also have a couple unshared pairs of electrons. Oops, we'll make it two like that. That looks bad. Oink. Oh no, what happened to my oxygen? It comes back. There we go. Ooh, that was close. Yoink, yoink. Okay, good. So that is water. Now notice it is not a lattice. It is just one piece that if I had little tiny hands and little tiny feet and little tiny eyes, that I could actually pick up this piece and hold it in my hand. Whereas if I tried to pick up the lattice, it'd be like a whole bunch of Na pluses and Cl minuses. Whereas with water, I could pick up one piece of water and there'd be two hydrogens and one oxygen there. Okay, so that is my covalent. Now let's go back and see if we can answer our question. Consider NaCl and H2O. What kind of bonds do we have? Well, I recognize that Na is a metal. I recognize that Cl minus is a nonmetal. When I have a metal and a nonmetal, I'm thinking ionic. Here, hydrogen is a nonmetal. And remember, even though hydrogen is up here, that is still a nonmetal. My hydrogen is a nonmetal, right? Good. And oxygen is over here. It's a nonmetal. So when I have two nonmetals, nonmetal and a nonmetal, what's going to happen? I'm going to have sharing of electrons. That means I have a covalent bond, and I'm going to form a molecule, right? Cool. Moving forward. Calcium oxide and methane. All right, you pause me and you tell me the answer. Welcome back. Here we go. Calcium. What do you know about calcium? I look at calcium, and where is calcium? This is on what side of the periodic table? It's on my left. In fact, it is what we would call what? An alkaline earth. What? Metal. Aha. So calcium is a metal. Oxygen is a non-metal. If I have a metal and a non-metal, this is going to be ionic. Carbon. Where is carbon? Carbon is right here. That is certainly a non-metal. If I have a non-metal and a non-metal, I'm going to form a what? Covalent bond. Good. Moving forward. Let's see, where do we go from here? Zoink. Okay. Let us consider, let me clean this up. Secret information there. Let us consider the following bonds. I have a GAO, an HH, and a CH. Predict the bond type. Okay, so let's come back to our notes, and let's add some stuff over here about predicting. Predicting bond type. Can we predict bond type? Yes, we can. How? We can use the electronegativities. You guys remember that? Electronegativities of each atom in bond to predict bond type. Now, specifically, how do we do this? I can look at the difference. The greater the difference, and I'm going to use delta as an abbreviation for difference in the future. The greater the difference in electronegativities between my atoms, the greater the difference, the more ionic the bond is. The more ionic the bond is. Now we can state that a different way, can't we? Sure we can. We can say what? The lesser the difference in my electronegativity, the more covalent. The more covalent the bond is. Because things are either, I mean, really it's a continuum from covalent to ionic. Over here, well, let me draw a nice little picture. Let's go over here. Let's make a nice little graph. Yep, and let's put my change in electronegativity, and let's say bond type down here. And let's say that this is covalent. Pure, we'll call this pure covalent, and we'll get into that in a second. Pure covalent, and we'll say this is ionic, complete ionic. Good, and we'll say 0 going up to, I don't know, what, 2.5, something like that, maybe 3. And what we have to understand is there's a continuum. It's not like things are ionic or covalent. They have a covalent nature, an ionic nature, percent covalent, percent ionic. When my change in electronegativity is 0, we have pure covalent. And as that increases, as my change in electronegativity increases, it becomes more and more ionic. And so we would say this is what? Increasing ionic character. Good, but I can also look at this a different way. When I'm at 0, what is my percent ionic? We say it's 0% ionic, and I could go like this, right? And this would be increasing, what did I just say? No, I just did ionic. Oh, I'm completely confused. We're going to go this way, right? I start up high here. No, I would just leave it like this. Increasing, this is a mess. Yoink, yoink. Let's just do this. Here we go. This is increasing ionic character. And so the opposite, sorry about that, folks, this would be increasing covalent. There we go. Sorry to confuse you there. I confused myself. As my delta En becomes big, I increase my ionic nature. As my delta En becomes small, I increase my covalent nature. Now there's some rules of thumbs, right? And here are the rules of thumb. Rules of thumb on this. Number 1, when my delta En is equal to 0, we call that pure covalent. And what is pure covalent? Pure covalent is equal sharing of electrons. Okay? Good. Rule of thumb number 2. Delta En greater than about 1.8. Most people would say if it's greater than 1.8, we can call this ionic, that the bond is ionic. And really, anything else in between, anything between 0 and 1.8, you can call polar covalent. And what does polar covalent mean? It means unequal sharing of electrons in the bond. And remember, we're talking about in the bond, we're talking about bond types. Now, like I say, these are rules of thumb, and depending on the book, you might see different interpretations. And don't get too tied into the number like 1.8. If I have 1.7, are we going to say, ooh, that's polar covalent, and then 1.8, it magically becomes ionic? No, because remember, we have this increasing ionic character where 1.8 might be here and 1.7 is here, and there's not much difference in ionic character between 1.8 and 1.7. We just tend to announce to the world that it's ionic when we say that it's 1.8 or 2.0. Don't get too tied into this. This is something that at an intro chemistry level we tend to teach, but as you get into deeper chemistry, that becomes less and less important. Okay? So, back to our question. Holy cow. Good. How do I predict this? Well, I need a table of electronegativities, and look at this. Yahoo! There it is. Okay, so what did we have? We had germanium and oxygen, right? Where's germanium? Right here. It looks like it's a 1.8. Oxygen is a 3.5. So I have a 1.8 and I have a 3.5. What's the difference between those? It looks to me like it's a 1.7. So I have a 1.7. What do you guys want to call that? Well, I would call that probably polar covalent. But it's right on the border, right? It's almost ionic. Good. Let's go to the next one. HH. HH. Good. Let's look at HH. What is H? 2.1. HH. 2.1. 2.1. Hey, what is that? The difference is 0. If it's 0, what is if it's 0? We call it what? Pure covalent. Or non-polar covalent, meaning equal sharing. Good. And the last one was, oops, here we are. The last one was what? CH. So let's look at carbon and hydrogen. What's carbon? Carbon is right here. It's a 2.5. So with C and H, well, let's move it over here. CH 2.5, 2.1. My difference between the electronegativities is 0.4. So what am I going to call that? I'm going to call that polar covalent because it is not 0 and it's less than 1.8. Okay, here we go. Why don't you guys give this one a shot? Chlorine, chlorine, sulfur chlorine, and zinc chlorine. Pause me and bring me back when you have answers. Well, chlorine's a piece of cake, right? Because chlorine, let's clean this up. Zinc, I love this magical thing. Woo, woo. Chlorine, here's chlorine. So chlorine, it's a 3.0 minus a 3.0. What do I get? 0. That means it's what? Pure covalent. Good. What's the next one? SCl, sulfur and chlorine. So where's my sulfur? Oops, I just covered up my sulfur. Sulfur is right here. It's a 2.5 and chlorine is a 3.0. So I have sulfur 2.5 and chlorine is a 3.0. By the way, we're always looking at the absolute value here, aren't we? There's never a negative. So it's a 0.5 difference. 0.5 we'd say is polar covalent, meaning my electrons are not shared equally. And then my last is what? Zinc and chlorine. Where's my zinc? Zinc is right down here. It's zinc 1.6. Chlorine is a 3.0. 3.0 looks to me like, what is that? 1.4 difference. 1.4, so I'm going to say that is polar covalent. That's what I would predict, that it is polar covalent. Good. Questions? Excellent. Moving on to the last one. Consider CuCl. Is this polar covalent or ionic? Okay. CuCl. I think we should be able to answer this, right? Cu is 1.9. 1.9. Cl is 3.0. And I believe that is a delta En equal to 1.1, right? So that's what I would say, that is polar covalent. Excellent. Good. So what do we come over here? What is this? I would say it is polar covalent. And you know what? I would be wrong. Wait. How can I be wrong? I just did these numbers. It's got to be polar covalent. No. What is that? What do those numbers help us do? Predict. That's all that does. Those change in electronegativity are only a guideline. They help us to predict. What I like to say in chemistry is reality always wins. And what do I mean by that? Well, we have a whole bunch of things that we use to predict, but if it looks ionic, if it tastes ionic, if it smells ionic, then it is ionic, even if it has a delta electronegativity of 1.1. And the facts are that this guy makes a lattice, right? And if it's a lattice, what am I thinking? I'm thinking that it is ionic. And not only that, it has all of the characteristics of an ionic compound, meaning it conducts electricity when it's molten. It has a high melting point, high boiling point, and all the indications that in reality it is ionic. So the real answer is that this is an ionic bond. And why is it? Why is it? Because that's what nature is. And the reason I wanted to point this one out to you is always remember, our electronegativity differences only help us predict bond type. It doesn't mean it is a certain bond. Reality tells me what the bond really is, and by reality that means I look at the properties. If the properties are ionic, then guess what? It's an ionic compound. Okay, I think this is time to quit. Hope we haven't gone too far. See you later. Bye-bye.